Let's
Thanks so
start.
much, Tufik and Alec, etc., for inviting me to this exciting conference that is hopefully will last for many more years. This is the first edition. I was fortunate to be a speaker as the first one, and I'm happy to come again. The original title was Why Counting Counts, and the original abstract was Counting Counts Because It Counts. But this is a tautology, so there's not much I can say. This is so self-evident. So I really tricked you. It was only a placeholder, and the new title is The Method of Guess and Check. And the new abstract is Proofs Are Dead, Long Live Algorithms. I will give a few examples of my favorite algorithm, Guess and Check. So as you may know, my philosophy is keep it simple. And what's nice about what I'm going to present, the statement of the theorem, some of them conjectures, could be explained to maybe a 9-year-old. But first, let me share with you 3 disappointments. The first disappointment was, so I know that I'm very sensitive, but algebraic combinatorics did do a good job in bringing combinatorics into the mainstream. But once it got so fancy, it forgot its roots. So a very big disappointment happened 5 years ago. I'm still trying to get over it. The Journal of Algebraic Combinatorics, founded by Ian Goulden and David Jackson and Chris Goldfield a long time in the 1940s, decided a few years ago to become Diamond Standard. Diamond Standard is a very good thing that is free access and everything, but as bad as the publisher's greed is of trying to make money out of this, is the attitude that the ALCO editorial board took. And this is manifested as that I was invited, specifically solicited, for a special issue of the Goulden-Jackson issue for the algebraic combinatorics. It used to be called Journal of Algebraic Combinatorics, but then they had a rebellion and they dropped the word journal and had a diamond free, whatever it's called, diamond standard, and very self-righteously say, oh, we're really free and everything, but they sinned in something by snubbing elementary statement, elementary theorem. So this is a special issue of ALCO that I was invited to contribute. As you see, it's not here because the paper that Manuel Carros and I submitted, that in my humble opinion is better than any of the papers in this one, was this one. And I explain why this paper is better than any of them. And this was not even sent to a referee. It was desk rejected by the editor-in-chief. They just took a quick look at it and say, we can understand everything. See, we can understand everything. It's not quote unquote important enough. And they send me a snotty rejection slip. A preliminary investigation showed that your paper is unlikely to meet the levels of originality that we and depth that we are seeking. But let me just briefly tell you, and one of the conjectures is still open. So let me just briefly, in terms of time, explain these two conjectures. As I'm sure most of you know, Young tableau is a way of arranging the integers from 1 to n so everything along every row is increasing and every column is increasing. So let's take, so if you look at the specific shape n, then you have the famous Catalan numbers. The number of standard Young tableau of shape n are the Catalan numbers. And if you do number of standard Young tableau of shape n, a 3 by n rectangle, you have also a beautiful, nice closed form formula, sometimes called hypercatalan. So this is very nice closed form. So let's look at such a 3 by n shape. And let's look how many standard Young tableau are they. This is easy. Beautiful closed form formula. If you want the 10,000th term, plug it in. You get a huge number in 1 second. Maple will give you a very, very big number. We'll take up the whole screen, but it will take 1 second. Now tweak this very problem. Very simple one. Suppose you forbid that you have I followed by I plus 1. In each of the 3 rows, if you have, for example, in row number 2, you have 8, you cannot have 9 right after it. In other words, every run has to be of length at least 2. So this is a very small tweaking. And this is a sequence that starts like this. 1, 1, 5, 15, and the 200 terms are here. So Shalosh can get 200 terms. And Manuel Carlos, with a much bigger computer, can get roughly 1,000 terms. But nobody can get 10,000 terms. So this is, in my humble opinion, this problem. And also, morally, as many of you know, this was coined by Richard Stanley in 1980, the notion of p-recursive. Many sequences in combinatorics are so-called p-recursive, meaning, the Fibonacci numbers satisfy a second-order recurrence. F sub n equals f sub n minus 1 plus f sub n minus 2. But with constant coefficients. And the factorial and factorial satisfies a first-order linear recurrence. A sub n equals n times a sub n minus 1. So a p-recursive sequence is the next best thing, is a linear recurrence with polynomial coefficients. And once you have it, even if it has a order 100 and the coefficients have degree 100, with a computer, you can easily get the 10,000 terms. But Manuel Carlos, with his fancy program, realized that it's very unlikely that Z of n is p-recursive. So that's a challenge to Michael Wallner and other people who make a living by proving that something is not D-finite. P-recursive and P-finite are related. That's synonym sometimes. So this is the first one. And this conjecture is more interesting than any of the papers that were published that got accepted in this one. And this is another sequence, A sub n. Now, often, if a sequence is p-recursive, it has nice asymptotics. And this, numerically, has beautiful, very precise asymptotics. And I'm offering a $200 donation to the OIS, and maybe I make it $400 now, for anybody. Still open. And nowadays, being published in a peer-reviewed journal is a complete formality. This paper exists in the archive and, more importantly, in my personal journal and also in Manuel Kauer's thing. Anyway, look at this beautiful asymptotics. G of n, in other words, the number of standard Young tableau of shape n, such that every row can never have two consecutive integers, is asymptotic to some constant, which I have no clue, is maybe expressible in terms of pi and e or whatever, times 8 to the power n over n to the power 4. And I'm always sure it's correct, but I have no proof. By the way, if you remove the restriction using Stirling's formula, this is 27 to the power n over n to the power 4. So let's replace the 27 to the 8. And to the other sequence that I'm not mentioning now, this is also similarly defined. You also have beautiful, and you're welcome to look at my paper at your leisure. So that was the first disappointment 5 years ago. And then I wrote an opinion about it, but you're welcome. So everything, if you go to my webpage, my homepage, you click on personal journal, all the links are there. And eventually there'll be a link to the video once it comes out. Now, a second disappointment is not my own paper. It's so-called self-proclaimed art gallery director Patrice Osona de Mendes rejected Xiandong Wen's artistic masterpiece. And this got me even more angry at the narrow-mindedness of this and very snotty rejection of so-called highbrow combinatorialists. So, and I know it's not nice to talk ill of anybody, but if there's anybody I'm disappointed at, is Patrice Osona de Mendes. It's not the first time. As I noticed that a few years ago he rejected another paper of my student for the same formula. It's not good enough or deep enough or important enough for our journal. Anyway, this was Xiandong Wen's beautiful solution of a long-standing open problem in combinatorics. As many of you know, Young's lattice is just the set of all integer partitions, but it has a natural order. So if you look at all the partitions with at most 5 of length 4 in the same journal, it was still a good journal, European Journal of Combinatorics, Lindstrom, and did it for the Young's lattice of 3 by n, and Doug West did it for 4 by n, but there was a big open problem to do it for 5 by n. So 37 years later, Xiandong, and here his opinion describe the history. I don't have time to tell you. And then was the report by the referee report. Very snotty. It's okay paper, but not good enough for a journal. This is a major open problem to get a symmetric change in composition. This is a way of arranging the lattice into symmetric chains. Richard Stanley famously proved that for an arbitrary L of 5n, there is a central chain the composition, meaning, and this proves the so-called Stirner property, but never mind the details. So this is a Snyder review. I don't have time to read it, but you're welcome at your own. Anyway, the paper itself is here. Yeah, it's in the archive, and luckily it got published in a much better journal than what the European Journal of Combinatorics is now. The ECA, Enumerative Combinatorics and Application, by the much better and nicer person, Tufik Mansour, got accepted. So, in some sense, Patrice, Osana, whatever, did a favor. It got published at a much better journal than it would have if he would have accepted it. Anyway, and look briefly, it's a beautiful. And then when I complained to Patrice Osana de Mendes, he very statically said, I have a responsibility. I'm a director of an art gallery, and I only want to put in my gallery the best art. And no offense, Patrice, I looked at you, quote unquote, art. It's so boring. Borel measure and this, and just to understand it, you have to go to grad school. This is something you can explain to a 5-year-old, but the construction is like a big cathedral. It's a beautiful, beautiful, very intricate, and of course, computer assisted or even computer generated, but with lots of very sophisticated program. 37 years was an open problem to construct a symmetric chain decomposition explicitly for the Young's lattice ELF. So this is my second disappointment. So now we go to the next disappointment. David Jackson and Bruce Richmond, who I really used to admire, a few years ago, famously announced that they have a computer-free proof of the 4-color theorem. Then Terry Tao and others first endorsed it, and then Terry Tao and many other people looked at it and found some issues, and it was retracted, luckily. But then they retracted it. And the current version from December to December 2003 is still on. And this is a very big disservice to mathematical knowledge. My dream is that one day you will not need peer-reviewed journal. The whole system of peer-reviewed journals is very flawed, very elitistic, and has all the human frailties. In an ideal world, there'll only be papers on the archive, and all the review refereeing will be open, zero blind. And this issue will be like when you have comments. So this is complete antiquated system of the peer review journal. So when I have a paper by myself or with my computer slot B1, I never bother to send it to a peer review journal. It only goes to the archive and sometimes not even there. But it's the internet, it's a publication. And I say, don't bother, it speaks for itself. But the fact that a obviously erroneous paper still exists, not retracted, is very disappointing. So it looks very superficially, it looks very convincing. But if you look at the asymptotics, it's complete gibberish. I'm not an expert on asymptotics, but I asked some experts one, and they confirm that this is not even wrong. It is complete gibberish. And I wrote email to David Jackson and Bruce Richmond, and I copied the chair of Waterloo, and I begged them to retract the paper. But no response. They didn't even say, thank you for your suggestion, but we prefer to keep it the way it is. We still stand by it. But no, it's just the cold shoulder. They did not. This. So I think this is a very, very disturbing and very, very disappointing. And it really ruins the reputation. David Jackson and Bruce Richmond, both of them, has such a good track record. They contributed so significantly. So it's just so sad that they stand by it and don't retract the obviously erroneous paper that they did about the four-color theorem. So it would have been more. So, okay. You can read the opinion later on at your leisure. Okay, so the David Jackson and Bruce Richmond alleged proof of the four-color theorem was a real lemon, but you can always make lemonade out of lemon. So looking closely at the paper, I learned something new. So this paper was not a complete waste. It's not a breakthrough. It's not proving human supremacy. That, to be honest, I was always afraid that one day a human would prove the four-color theorem, since, as you may know, I'm rooting for the computer kind. In my opinion, if a human can prove something, it's ipso facto, not the tip. So no offense to Andrew Wiles, but Fermat's theorem, in retrospect, in hindsight, is not bad for a human. It's pretty deep for a human, but in the eyes of God, it's pretty shallow. So I was always afraid that one day the proverbial smart high school student would come with a simple proof of the four-color theorem, similar to the very simple proof of the five-color theorem. And then I was a little bit nervous, to be honest, because I'm rooting for computer kind. Well, David Jackson and Bruce Richmond then came up with a typo, Richmond. So the main idea in the failed attempt of Jackson and Richmond was using a fundamental theorem paper of the hero, also my hero, W.T. Tutt. W.T. Tutt is a very, very important graph theorist. Also, he was important in finishing World War II, along with Alan Turing and my I.J. Good, another hero of mine, and my mentor, Joe Gillis, unfortunately all gone. They cracked the Enigma code in the British Bletchley Park, and well, lots of smart people were there. So W.T. Tutt did contribute a lot, but the paper that is one of his most important paper was counting some planar maps. So I looked at this paper. I don't have time to go through his paper. And this was an important ingredient in the alleged failed proof of Jackson and Richmond. So he wanted to count some maps. Never mind the definition. That's not important. The important is, I'm illustrating now my favorite algorithm, as I said, guess and check. So the remaining of the talk is 3 case studies in using guess and check. 2 of them inspired by the failed attempt of Jackson and Richmond. So W.T. Tutt in a seminal paper here, it's a hot link. I stole it and put it in my own website. So here it's a classic paper on counting maps, a census of planar triangulation. So it's a beautiful paper of a genius, and he used generating functionality. By the way, Tutt was one of the pioneers in the technique, in the very important tool in combinatorics and elsewhere called generating functionality. I would give him, he's one of the founding fathers, along with Marco Zeilberger and George Polya. I would rank him as a founding father of generating functionality, using formal power series, not convergent power series, but formal power series that are much more user-friendly than the one you learn in Calc 1 or Calc 2. Anyway, never mind, you want to count the 2 parameters. In fact, you only want to get a certain 1 parameter thing, but you need 2 parameters. So you need a bivariate generating function. I call it the catalytic variable. Even if you want to only count something that only depends on n, in order to facilitate the counting, you need to introduce another parameter that you don't really care about. You may care about it later, but it's not that relevant, but you need it. And then at the end of the day, if you are an ingrate, you just go back and plug m equals 0. Anyway, so this is a bivariate generating function. So this counts certain maps with n. 2n triangles and whatever. And the other parameter is m. But that's not, once again, the details are not important. It's the technique. And then when you plug in y equals 0, you get g of x. And then that's the related one. But then he worked pretty hard to get, using human ingenuity, that I'm sure in 10 years a computer will be able to do from scratch. So this part will be, but until further notice, we still need the genius of, here it is, 3.8. So looks like a quadratic equation. Psi square, psi, but look at g. But g is just shorthand for psi, open parentheses, x comma 0. So this is a functional equation. So using the formula from 9th grade for solving quadratic will not help you. And then there is a much fancier way that, no offense to the people who like it, that I don't like it. It's called the kernel method, that using sophisticated complex analysis and using lots of human quote unquote ingenuity can also presumably probably can solve it. But keep it simple, stupid. So the method that Talosh B. Echad and I did was to solve this functional equation completely by guess and check. And now that we have computers, of course, W.T. Tutt didn't have a computer in 1962. So he had to work 3 pages plus losing his very extensive knowledge of previous combinatorics. And he worked very hard to solve this functional equation. So let's go back to my paper. Okay. By the way, this paper is only quote unquote in the archive in my personal journal. I don't bother anymore because I'm fully promoted and I stopped submitting to the NSF because it's so much trouble. So I'm a free agent and I don't need to get a chance of being rejected by people like Patrice or Sana Elemendes. But unfortunately, I still have a lot of students and collaborators. So with them, I still have to put up with peer-reviewed journal. But try to submit to friendly journals. For example, the ones that accept email submitted. Most journals nowadays are so bureaucratic. You have to sign up and have a password, and it's so bureaucratic and so inhumane. And then you get a rejection by a computer, and I really hate it. But a few exceptions, and one of them is ECA. So I really, next time you have a good paper, I really recommend you submit it to ECA. In fact, now I have one paper with collaborators pending. Anyway, so let's go back to the functional equation. So this is the functional equation. So once again, let me remind you. Oops, sorry. Psi of xy is some formal power series in x and y. Now let's abbreviate. Little g is psi of x comma 0. And lo and behold, if you can easily program it on the computer, get the first 30 or 40 terms in the Taylor expansion with respect to y. Then you plug in y equals 0, and lo and behold, just staring at it, you can easily conjecture this beautiful, beautiful closed form formula for the coefficient of x to the power n. And this has a combinatorial graph theoretical meaning, counting the number of maps that the great W.T. Tutt was interested in. So he was interested in counting certain maps with 3 triangles, I think, and got a beautiful, explicit closed form formula. But proving it is not so easy, and it took the genius of W.T. Tutt to prove it. But nowadays, with Shalosh Biachad, it can be done in less than a second. So here you have a maple package that you write once and for all. I call it tat.txt. So all you have to do after the conference is over, go to my homepage and download. Hopefully you have Maple. So you save it. It's already saved, but I save it anyway. And now let me stop sharing and start sharing Maple to be like a demo. So tell me if you see the Maple scheme, Alec. Alec, do you see the Maple scheme? Alec, what did I write? Alec?
Yes.
What did I write in the Maple scheme?
Hi, Alec.
Okay, thank you. Okay, so you do restart, you go to restart, read cat.txt. And you do, and Ezra in Hebrew, it means help. So the main one to solve the functional equation is the procedure GAP. Or it takes the functional equation in the format. So this proves in 1 nanosecond what Tutt worked very, very hard in 1962. Let me explain. And you're welcome to play with this later on. So the input is you have two variable formal parameters, psi and g. And psi stands for the formal power series in x and y, and g stands for psi of x0. So this is telling Maple what are the meaning of this. And this is just a humble polynomial in four variables, x and y, the independent variables, and psi and g. This is, but they are intertwined. It's not a simple nice-grade equation, but you have to solve it. And how you solve it? You copy and paste it, and here, in less than a second, it outputs a pure algebraic equation for G. So it eliminated psi. So this means that the formal power series G of x that is chock full of the original combinatorial meaning, counting certain maps of triangulations that WT type was intersected, satisfies a very simple equation in Maple. If there is no equal 0, it means equal 0, namely g to the power 4 times x cubed plus 3 times x squared and blah, blah. So, and once you have this, you can crank out many terms, but also using by now routine computer algebra tools, GA-FUN, you can easily get the sequence itself. So if you want, so, and you can get, so the explicit expression can also be derived completely automatically. And everything is automatic, and everything is done by Shlomo Biachal after the initial effort of program it. Oops, sorry. Yeah. So copy. Yeah, here we have all the terms. And also for this means also the coefficient of y squared, y squared. So this is, everything is automatic. So let me, so that's the point, that in guess and check, you don't have to be clever. You have to be meta clever to write some code, and using today's powerful computers, you can save WT lots of problems. So let me now go back and stop sharing and share the Alex, do you see the paper solving functional equations?
Sure, I do.
Okay. So this is the first lemonade I made from the failed attempt of Jackson and Richmond. The second, I mean more briefly, is what I called the Jackson-Richmond 4CT 4-color theorem constant. Is exactly 10/27. So they went through this erroneous but very circuitous argument in the failed attempt. They needed an important ingredient in their failed attempt for the proving without computer the 4-color theorem is the following innocent lemma. By the way, this is exactly as the G of X of the previous paper, written in slightly different notation. So for their alleged proof, they needed the following one. Take this very innocent looking formal power series, square it. It's another formal power series whose coefficients are some convolutions, and extract the coefficient of x to the power n. then divided by the coefficient of x to the power n in g of x, namely this guy, takes a limit as n goes to infinity. And they needed that this is a positive constant, I think bigger than 1. So that was a crucial thing. And they went to lots of erroneous effort to erroneously compute it, and it had to be some weird transcendental number. But with a little bit of computer algebra, they could have do some fact checking. So it turns out that this constant, they desperately needed, the lemma was that this constant is positive. And that was crucial for their thing. So this lemma is right, but the determination of the constant was completely erroneous. And it turned out that it's not transcendental, not even algebraic. It's just 10^27. And the proof is, with today's computer algebra tools, it's purely routine. First, it's very easy to program it and take the limit and get it. So they could have done it if they knew a little bit about computers. Which I'm really, really disappointed with this. But something much more better. Forget about the limit and go to infinity. This is a beautiful, explicit formula for the quantity itself before you take the limit. So take this former power series that counts maps, and then you extract it, and then ask the computer to crank out the first 30 terms of this ratio, the coefficient of g of x quantity square, the coefficient of x to the power n divided by this, and crank out the first, and then fit it, data fit it with a rational function. It's not guaranteed a priori that you have a rational function. And indeed, if you just take a random g of x, chances are that it will not be a rational function. It will be something much more complicated. It's definitely going to be p-recursive, but it will not be a rational function. But in this case, but once you have a conjecture, it's routine to prove it. One way is via the Zeilberger algorithm, but the other way is via the Zeilberger algorithm, ansatz. Anyway, but computers are so good, they're so flexible. Once you do one problem, you can do many. So what happens if you replace the 2 by R? So you can go up to any R you want. So in this maple package, it computes these quantities explicitly, and then the human or the computer can take the limit, and you have when I is 2 is what we already have, but when I equals 3, and this and everything is here. So this is the second lemonade out of the Richmond. I'm almost done, but the final one was not really combinatorics, but very nice use of computer algebra. And you're welcome. It's a very nice story, and very soon will be written up by Joseph Howlett in Quanta. So let me stop sharing because I don't have time to actually give you details, but let me tell you the story. I'm almost done. Yeah. Okay. About a year ago, an Italian fluid dynamics expert by the name of Alberto Maspero wrote me an innocent email. He defined some rather complicated combinatorial quantity, a weight on certain, every integer partition has a certain weight, very complicated. And then he did some summation over all the weights over all the partitions there. And he needed to prove that these two summations are never zero. If he can prove that these two summations are never zero, this would imply a long-standing open problem in the study of ocean waves that I admit I don't know much about, but I do know about summation. So if you do it naively, they did it up to the case 21, because the summation, the summand, the set over which you sum all the weights is exponential growth. So eventually you can only go so far. So they proved this special case up to 21. Now using dynamical programming, my computer and I were able to get another reformulation that is no longer exponential time, it's polynomial time. So we can compute 30,000. But 30,000 is still not infinity. They want to prove it for every p. But then Charlotte's conjectured a much simpler second order recurrence equation that make it even possible to compute it, to verify this conjecture up to 10,000 terms. But 10,000 terms is still not infinity. But then, sometimes, but not always, a second order equation can be solved, quote unquote, explicitly. And Mark van Hoyts is one of the greatest experts, maybe the greatest expert in the world of doing it, a disciple of Michael Singer. And that, a shot in the dark, I wrote him an email, I offered to donate $200 to the OIS if he can, quote, solve it. Once he gave the explicit expression as a non-terminated sum, the proof was completely routine. And also we needed Christoph Kutschan's a beautiful package to prove that the other formulation that I did is equivalent to the original one. And the expression that Van Hoyts came had another parameter x. So it's very complicated, but when you plug in x equals n plus 1, you get exactly what was needed that happens to be non-zero. So it's an example of the unity of mathematics and why people should not look down on anything, even if it looks simple. Thank you very much.